Switch out a picture.
Okay, so our plan for today is as follows. First of all, I'm going to talk briefly about any homework questions that you might have. In particular, I would like to talk about how to organize your algebra so that it's less error-prone. Yeah, for you. And then we're going to talk about cited derivatives. Which is our main story and will be the story for the next 3 days, really. Okay. In particular, I'd like to take a look at one of them. I believe it was number 31. That went a little something like this. Is this correct? You guys remember doing this problem?
Yeah. Yeah.
Do I have the top and bottom correct?
Mm-hmm.
Okay, all right. What I found when I was going through the homework was that all of you were getting the calculus part right, but then the algebra was tripping you up. So you may have noticed that I made some notations on yours that you needed to redo it. It was in almost every case, it was because the algebra, not the calculus. So the quotient rule part's happening, but then when we go to simplify it, bad things occur. So I want to make some observations about this. We're going to go ahead and use quotient rule on this. Give me the quotient rule.
Square root of x plus 1 times the derivative of x, square root of x minus 1 minus square root of x minus 1 go to the derivative of the square root of x over square root of x plus 1.
Yep. And now here comes the first observation. There's something wrong already. What is it? What is that called? Parentheses. Exactly. You see this phrase? I do not think it means what you think it means. Look at what it says. What you meant, but I did this because I had some people doing this. What he meant was low d high less high d low, right? What I actually wrote on his behalf was the square root of x plus 1 times the derivative of blah, blah, blah. Order of operations is a real thing. And when you write something that does not say what you mean, then it doesn't mean what you intended. So if we want to say x plus 1 quantity times the derivative of root x minus 1, then we must explicitly use parentheses to override the order of operations. That's what parentheses do. So this is our first thing. Please remember to enclose your low and your high functions in parentheses if they have multiple terms, because otherwise what you write is not what you're intending. That's the first thing. Now, second thing, carry on from here.
Times 1 over the 2 square root of x.
Good.
Minus 1 over the 2 square root of x.
Yep. Now, here's the second thing. In the bottom here, notice, unless it is a matter of great necessity, I am not going to simplify the denominator. Unless it is a matter of great necessity, I'm not going to simplify this denominator because it almost never gives me any additional insight. This is easier to work with than x plus 2 root x plus 1. Yes? Mm-hmm. Unless it is a matter of great necessity, I'm not going to simplify this denominator. If I really, really need to. Necessity. Yeah. Yep. Okay, so the next thing is don't simplify unless you must. Now, the third thing is a matter of practical whatever. Don't simplify unless you must is actually a great slogan for life. This expression right here, from a calculus point of view, is done. All of the derivatives that need to be taken have been taken. Okay. So it's a great slogan in life. So from a calculus point of view, we're actually done here. And if you're working on a test or a quiz, and I have not already said simplify, and you don't need this for anything, don't simplify. Stop. You're done. Leave it. Tell your inner simplifying nerd to be still. Okay. Unfortunately, when you're on your homework, there is always a reason to simplify. And that is because once you've worked a problem, you are going to check your problem. And when you look in the back of the book, you're not going to have this. You're going to have the simplified answer. So unfortunately, on your homework, you're going to have to practice simplifying. That's actually not bad. It's good for you like broccoli. And specifically, it's good for your algebra. Calculus is good for your algebra because it puts you in these situations where you have to simplify these whole things. Okay. But from a test or quiz perspective, stop here unless you need to move on for some reason. Okay? All right, now, how to move on and simplify using the least amount of effort possible. Factoring is your friend. Consider common factors that can come to the outside. So a basic simplification strategy, look for common factors. Another related simplification strategy, clear the fractions. If you have a complex fraction. I look at this situation and I say, hey, you know what? I've got a common factor of 1 over 2 root x. I am going to pull that factor to the outside. And when I do look at the lovely thing that happens, I'm left with root x plus 1 minus root x minus 1 all over x plus 1 quantity squared. And this is root x minus root x plus 1 minus negative 1 is plus 2. Again, continuing with the theme of common factors, I notice there is a common factor of 2. And this gives me my final simplified answer, just like so, and we are done. That wasn't so bad. And the reason it wasn't so bad is that instead of simplifying here, and then simplifying again, and then instead I pulled out the common factors again. That made my life a whole lot simpler. Does that make sense to everybody? Yeah. Yep. You cleared the fractions by multiplying top and bottom by 2 root x. Yep. And then get it on. If your answer really is different. This is interesting. She gets this answer. This guy right here. What's interesting about this is that I observe that this fellow right here and this fellow right here are similar to one another and yet different. And I wonder how all that happened.
So when we're like I'm using the color rule, or it has to be a
That's a really good question. Soon and very soon, we're going to extend the power rule to be able to handle situations like that. I'm not sure where the error is in this. Ah. Huh? No. Got it. Here it is. This is minus -1 times, that's +1. That should be a plus. Minus -1 times, good, that's minus,
Yeah, it's minus x
should be plus,
plus 1.
right here. That minus right there
Should be plus.
should be plus. Isn't that a -1? Yeah, that's a -1 from here. So, moral of the story, you took a hard way and it made it easy to make mistakes. You see what I'm saying? So take a simpler way. Let's take a look at one more, number 22. And in number 22, we have the derivative of, how does it go?
X plus 1 times x plus 2. Or x minus 1.
Now, if we do this according to the form that we have right here, let's do a little bit of looking ahead. If I take the derivative using calculus at this moment, I'm going to end up doing quotient rule. And for each of the derivatives of low and high, I'm going to end up using product rule. And it's going to be a pain in the neck. But if I consider the possibility of doing some algebra first, you've heard me say that before, right? Then I might be able to simplify my life. Does anybody see some basic algebra that can be done here? There's -1. What do you mean times -1? Never mind you. More basic stuff. What do you see here that could be done? I can multiply. Absolutely. What is x plus 1 times x plus 2? Yeah. And what is? Absolutely. Now, this is going to still require quotient rule, but it's not going to be nearly as yucky. So, low D high. What do I need to remember? Plus high D low. My other class, I ran out of room on the board for this. I started this all over a little bit further. And there is the calculus setup, quotient rule setup. Okay, let's walk through and simplify. Derivative of x squared plus 3x.
2x plus 3.
And derivative of x squared minus 3x plus 2. And what happens on the bottom?
Leave it.
Leave it. Thank you. Okay. Now, this is the worst that the problem is really going to be, right? And so, well, not quite, because what we're going to have to do is to do some distributing in order to get all of these terms. But let's be smart about the distributing. When we distribute, we're going to distribute our 2x to every term and our 3 to every term. And over here, same thing. But let's keep the subtraction as it is and subtract that whole thing. Then we can be smart about the terms that we are canceling. So, give me the distributive for the first set of terms. 2x times all that. What do I get?
2x cubed minus 6x squared plus 4x.
And for the next set of terms, somebody else? Plus 6. Very good. Minus, and I'm just going to put a parenthesis here for all these terms, and then we'll have this all over blah 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 squared at the end. Okay, so let me give you the distribution on these terms. Clara.
So x squared
Okay, here's my final bit of advice. See this big subtraction right here? Before I do any simplifying inside, I'm just going to observe, are there any terms that I can cancel outright? 2x cubed, 2x cubed. Gone. 4x. Now notice, minus 6x squared minus plus 6x squared will not cancel. They're going to combine. But the 4x and 4x, gone. Minus 9x, gone. And all of a sudden, my problem is half as yucky as it was before. Alright, now we can walk through and collect our terms. We have minus 6x squared, minus 3x squared, minus another 6x squared, and plus another 3x squared. Minus 12 plus 6 is minus 6x squared. That's not so bad. Plus 12, all of that over this guy right here. Huh, that's not so bad. Question? I recommend, now I'm not going to give you a lot of problems like this, but I would recommend that once you are done with the calculus part, all the derivatives have been taken. This is a perfectly good algebraic answer, unless you need it for some reason. Unfortunately, what we do with derivatives very often involves like setting them equal to 0 or something like that, and so then you have to simplify it anyway. So it's not much of a concession that I'm making, but it's a little bit, right? Good. Does this take care of questions you have about? Then let's talk now about cited derivatives. To get there, I want to take you back to this notation right here. Remember this? How did we pronounce this? The limit, everybody. The limit.
X goes to C from the left and
That's it. And what does it look like on the graph? We're going to have some function, some value C, and now I'm going to approach C from the left. And when I do, if that value is arbitrarily close to L when x is close to but less than C, then my limit from the left is L. And the same thing, these guys pronounce the limit.
X goes to C from the right and left.
And for this particular function, it appears that both the limits from the left and the right are both equal to L. And since the limits from the left and the right are both equal to L, then the two-sided theorem allows me to conclude that the limit as x goes to C of f of x is equal to L also. We call this the limit from both sides. Okay? So we were happy with this. Question. Does this mean that f of x is continuous at x equals C? Not necessarily. What additional piece of information would have to be true for continuity?
Left of C equals L.
Very good. So I can draw a different function that is not continuous at x equals C, but whose left and right limits are both L, so that the overall, or limit from both sides, is also equal to L. But I can draw a separate function so that the limit as x goes to C from the left is equal to L, and the limit as x goes to C from the right is, and the limit as x goes to C overall. Very good. And please notice that this is not equals D and E, which doesn't make any sense. This is just does not exist. Okay. By the way, what type of discontinuity did we call this?
Point.
Or removable. And what type did we call this? Jump. Very good. And it was because of the limits. Excellent. Now, it occurs to me that the derivative fundamentally is a kind of limit. Specifically, it is the limit of the difference quotient. And if I use the alternate definition to express that, then I'll set it up in a manner that is familiar to you. The limit as x goes to c of f of x over minus f of c over x minus c is equal to f prime of c. So this is our alternate definition of the derivative. And it goes with it a slogan. The limit of the difference quotient is the rate of change. Is the derivative. Okay? So far, this is all stuff we've done. But now it occurs to me that maybe I could put these two ideas together. Could I approach c from the left or the right on the difference quotient? And if I did, could there be some circumstances where I get different answers from left and right? Maybe so. Alternate definition. Here, let me spell it out, just to be clear. Better? Okay. So our picture was that I have some function f, and I have a point c, and I'm now going to compute the difference quotient as the slope of the line connecting these 2 points and when I compute the slope of the line connecting these 2 points and let x approach c, then what I get is the slope of the curve at that point. That's my instantaneous rate of change. In this particular case, it sure looks that way, doesn't it? But maybe, just maybe, that might not be the case. So to investigate that, I'm going to introduce a little bit of new notation. We're going to call the derivative from the left at c to be the limit as x goes to c from the left of the difference quotient. And we're going to call the derivative from the right at c, you know what, for the sake of coordination, I'm going to make this one blue. There we go. And then I'm going to make this guy red. The derivative from the right at c is going to be the limit as x goes to c from the right of f of x minus f of c over x minus c. And maybe these two limits are the same, and maybe they're not, depending upon the function. And if they are the same, then the limit from both sides is equal to that value. And in that case, we would say that f prime of c is equal to that value. So let's make this concrete. This is going to be our two-sided derivative theorem. We're going to say that the derivative at c is equal to some value d if and only if the derivative from the left equals d and the derivative from the right is also equal to d. Because if both derivatives from left and right, which are limits of difference quotients from left and right, are both equal to d, that means that the overall limit is equal to d, and the overall limit is f prime of c. So that's our theory. Now, how does this work out in practice? And for the rest of our time, we're going to do examples. Yes, sir. What if they are different? If they are different, then the overall limit fails to exist, does not exist. And we simply say that f prime of c does not exist. Because if it did exist, if it were some value, say 6, then both the limit from the left and the right, or the derivative from the left and the right, would both have to be equal to 6.
Or the, C on the left,
Mm-hmm.
if this,
Yeah. But keep in mind that x is approaching C here, so as x gets closer to C, then ultimately I'm going to end up with a tangent line like that. And if I approach from the right instead, I'm going to get the same tangent line. So for this particular graph, limits from left and right are both equal to 0. But I'll show you some examples that's not the case. So far, so good? Okay, let's take a look. Let's consider f of x equals the absolute value of x. And let us find derivatives from left and right at 0. First is our setup. We're going to take the limit as x goes to 0 from the left of the difference quotient. Yes, sir.
do we have slope of x?
I guess we'll find out. Substituting, we get this limit right here. We've seen this limit before. What is the limit as x goes to 0 from the left of absolute value of x over x? That is -1. Because no matter what value of x I pick, as long as it's less than 0, when I divide the absolute value of x by itself, then we're going to get negative. So there's the derivative from the left. Now, as we consider the derivative from the right, we're going to have the same difference quotient, but we're now going to let x approach 0 from the right. And if it's okay with you, I'm going to set up our difference quotient in abbreviated form because I know already how it's going to go. And when I do, what is the limit as x goes to 0 from the right? Positive 1. Now, what does this mean about my graph? This means that when I look at the graph, as I come in towards 0 from the left, what I get is that the curve is going in this direction with a slope of -1. And as I come in towards 0 from the right, what I get is that the curve is going in this direction with a slope of +1. And since these two sided derivatives give me different values, I can conclude, therefore, that f prime of 0 does not exist because the sided derivatives are different. Yeah. Yes?
What is the difference between the slope of the slope of tangent is 0 and so
Ah, very, very important. If the slope of the tangent is 0, that means that my curve has a nice, smooth, U-ish shape right here, or a nice, smooth shelf point right here, so that I can draw a tangent line that is horizontal, just like that. Okay? If my slope does not exist, could be a lot of different reasons for that, but in the case of the absolute value of x, it's because right here, I've got a sharp line. That's exactly it. So notice the difference. F prime is 0 here, F prime is 0 here, F prime fails to exist right here at the point. And that's actually what we'll cover tomorrow. How that works out. Does this make sense to everybody in terms of how we did the analysis? And the results are not too surprising, right? Okay. Now, let's consider what this looks like on a graph. Oh, before we do that, I want to consider okay. Now, at first, we think, oh man, I got to do my limit definition, but then something in the back of my mind says, wait a second, I already know f prime of x, don't I? What is f prime of x? And if f prime of x is equal to 2x plus 3, then what is f prime of 2? And if f prime of 2 is 7, then automatically the derivatives from the left and the right are 7 as well. So that if you know f prime, you know f prime from left and right. So that's our two-sided derivative theorem at work. And this is why we didn't really have to talk about sided derivatives before, because previously all of our functions had derivatives at every point that we considered. And so therefore we didn't need to worry about derivatives from left and right separately.
This means they can prove each other.
Yes, that's right. That's the virtue of the if and only if sign that we have right here. Right there. This goes both ways. If I know that the derivative is d, then I know both sided limits, and vice versa. Okay. Now let's take a look at graphs. Suppose I have a graph that looks maybe like this, and just for the sake of it, to make it look like that. And we're going to move this original function. Okay? So here's a graph of g of x. And we observe that right here at x equals 1, our graph takes a sharp turn, right? So we've got a nice straight line, and then right at 1, boop, we go the other way. And so what we'd like to do now is to estimate from the graph g prime from the right, left at 1, and g prime from the right at 1. Here we go, g prime left and g prime right at 1. To estimate, I'm going to fix g of 1 right here, and I'm going to draw myself a line that goes in the direction of g and goes to the left. This guy right here. And when I do, it appears that my line has what slope? Positive 1. Positive 1/2. So we would say that g prime from the left is going to be about positive 1/2. Same story over here. For the derivative from the right, I'm going to go to g of 1. I'm going to draw myself a line that goes in the direction of g, and it looks like that line has what slope? Exactly. And so these are estimates for my derivative at 1/2 and at negative 1/4. From this, can I conclude that g prime of 1 does not exist? Well, it looks like that might be the case, but it's hard to see because the graph can lie. So unless I know some additional information about g, I wouldn't necessarily be able to say. Maybe it exists, maybe not. Because I'm just estimating from the graph.
So what can I get from this conclusion?
Maybe g prime of 1 exists, maybe not. If I knew this piece of additional information, that g of x consists of 2 line segments, then that nails it. Because that means that my slope here not only is approximately 1/2, it is 1/2. and the slope here is negative 1/4. So if I knew that G, something about the shape of G, that it was 2 line segments, then I would know that G does not round off at here, but instead comes in and has a sharp corner, right at x equals 1. So if G consists of 2 line segments, then G prime of 1 does not exist. But if I don't know that about G, then maybe if I zoom in, then it sort of connects and rounds or something. See what I'm saying?
What if we don't have what information?
If we don't have that information, I can't say anything. I can only estimate these two. The same thing is going to be true if I have a table of values and I estimate from the left and from the right using difference quotient right there. Then I can provide estimates that the fact that they are different doesn't necessarily tell me anything. Good, great questions. Let's take a look at a fourth example. Let's consider here we have a piecewise function that I am asked to find the derivatives at the joint where the two pieces come together. Now I want you to understand why the joint is really special. Right here at x equals 1, this is really special because for x's that are less than 1, I just have a polynomial. My derivative for x is less than 1 is 2x. And for x is greater than 1, I just have a linear function. So my derivative for x is greater than 1 is just 3. But right at 1, the derivative from left and right can do funky things. And the reason for that is that my function is neither a quadratic nor is it a linear function. It is piecewise, quadratic in one direction, linear in the other. You see? So weird things can happen. And I'm going to have to carefully use the limit definition to find both of these quantities. Let me start with the derivative from the left. Okay, here we go. I'm going to take the limit as x goes to 1 from the left of the difference quotient. And first place that I have to be careful is with f of x and with f of 1. F of x is going to be obtained by using the definition of f for x's less than 1. Why less than 1? Because x is approaching 1 from the left. What is the definition of f when x is less than 1? The first one. Go ahead and give it to us. Exactly. Now, f of 1, on the other hand, is the definition of f when x is 1. And what is that definition? Same thing, but it's when x is 1. So it's actually 2. It's a number. And all of that is still divided by x minus 1. Does everybody see how we did the substitution? All right. So we're going to take our limit as x goes to 1, and we're going to have x squared. Yep, you see it. Since you see it, I'll go ahead and write it. We have x squared minus 1 up top, and so we have x minus 1, x plus 1. And now as x approaches 1, then we get what value? 2. And that is our derivative from the left at 1. So just to recap, this, we used the definition of f for x is less than 1. This, we used the definition of f for x equals 1. In this particular case, those happen to refer to the same piece. What about f prime from the right? Same song, second verse. We set up the difference quotient and take its limit. That's all good. But now definition of f for x's that are greater than 1, because I am approaching 1 from the right. And when I get to f of 1, this will be the same value of f of 1 as I used in the other one, because it is the definition of f when x is 1. And so that means automatically I can put 2 in here. What about the f of x? I go back, and I observe the piece that applies when x is greater than 1 is 3x minus 1. And so I put that piece in its place, like so. Yes, you see where it's going. That gives me 3x minus 3, which is 3 times x minus 1, which is equal to 3. And so what does this mean that my derivative from the left is 2 and my derivative from the right is 3? It means that when x is equal to 1, my graph has a value of 2, that's f of 1, but its slope from the left will be 2, like this, and its slope from the right will be 3, which is more like that. In other words, I'll have a sharp corner here, and in fact, my graph looks something like that. So it's a little hard to see the corner because the graph is only approximate, but there it is. You have a slope of 2 from one side and a 3 from the other.
So it's the, and the, one, it's kind
Exactly so. Because my derivatives from left and right are different values, f prime of 1 does not mean this. Yes, sir. F prime of 0 is easy because at x equals 0, my function is simply the quadratic polynomial x squared plus 1. F prime of 0 is equal to 2 times 0, which is 0. The end. So in other words, I can compute, I'll do this real fast, f prime as the derivative of each piece, 2x here and 3 there, for x's that are in the interior of each domain. But right at x equals 1, no derivative, because my derivatives from left and right are different. And we'll actually do this more carefully with some examples tomorrow. F prime of x is this. Well, it does for x is not equal to 1. It does for x is less than 1, and it does for x is greater than 1, but not for x equals 1.